Okay, so we got the technical difficulties out of the way. So hey everyone, my name is Richard Huang, and my project is related to a method to improve environmental remediation in subsurface porous media. So 22% of groundwater in the US is contaminated, and groundwater makes up about 50% of our drinking water. So there is a pressing need to find methods to clean up that groundwater. And one way to do that is direct injection of some cleaning solution into the groundwater to clean that up. The problem with that method is that underground environments are they're not just one homogeneous medium. They have different strata, and in particular, different layers accept flow differently. They have based on permeability differences. Some layers have high permeability, and some layers have low permeability, and fluid preferentially flows under laminar conditions towards the high permeability strata. So what my project found is that if we add polymers to the solutions that were flowing, we get a lot more flow into those low permeability layers. So just to start with, in regular flow, we use the Reynolds number to characterize, it's a ratio between inertial forces and viscous forces, with a low Reynolds number indicating laminar flow and a high Reynolds number indicating inertial turbulent flow. And we have some threshold between them that characterizes when that transition occurs. Now, when we add polymers to the mix, then we introduce an analogous Weisenberg number such that the Weisenberg number characterizes the strength of elastic forces, and at low Weisenberg number, we still have laminar flow because the flow is low enough that polymers are coiled, and they don't add anything to the flow, whereas at high Weisenberg numbers, past the threshold of about 2.7, at high Weisenberg numbers, the polymers uncoil and they enable flow streams to collide because of their elasticity. They can bend and stretch, and that causes flow instabilities that lead to elastic turbulence. So what I have here is it's a Healy-Shaw setup, and this is a model of a stratified medium. So at the bottom is a high permeability coarse layer, and at the top is a low permeability fine layer. I'm flowing in a dyed solution with polymers on the right and no polymers on the left at the same flow rate such that I'm able to achieve a Weisenberg number around where we would expect some instabilities to occur. And here's what happens. So what you'll notice is that when we don't have polymers in the solution, we get much slower flow in the fine stratum, and once we add them, we get a lot faster flow. And so we see that it seems to be the case that flow instabilities are increasing that flow speed in the low permeability layer. And we want to know why that's happening. So we created a parallel resistor model. Before I get into that, though, I want to talk about what we're basing this model off of. So prior experimental work and theoretical work models the pressure drop in a fluid flow across a porous medium through Darcy's law. So on the left here, I have a diagram of essentially our micro model of a porous medium. So this is a slightly different setup from the Healy-Shaw that I had in the last slide. Filled with, it's a transparent capillary, glass capillary filled with, a quartz capillary filled with glass beads of a particular known average diameter that is proportional to the permeability. We have some superficial velocity of flow going into the medium. We can measure the pressure drop across the medium. We have some fluid viscosity, and we have a length up for the medium. So once we add polymers into the mix, we see that we see higher pressure drops. And since the medium itself hasn't really changed and we're still flowing the fluid at the same speed, then naturally we must be seeing, based on this Darcy's law model, we must be seeing a higher apparent viscosity. What we do is we take the ratio between apparent viscosity and what we would see from a Darcy's law baseline to have some idea of the relative increased pressure drop from adding these polymers. So in previous experimental work, by imaging the flow at the pore scale, I don't want to go too much into the details for that, but we're able to derive this model for flow for the development of elastic turbulence in a homogeneous medium. And that aligns with these experimental measurements that we have. We measure the pressure drop at a certain flow rate, convert the flow rates into a Weisenberg number, convert the pressure drops into this reduced apparent viscosity, and we get this normalization. So we have this homogeneous medium model. Now, the model that is involved in this work is based on two observations from the Healy-Shaw setup. First is that there was a lot less vertical flow, like cross boundaries, compared to just within the same medium. And we capture that by essentially saying that the layers are their own homogeneous medium. And the second thing is, with the Healy-Shaw setup, we have a single source of flow. It goes and distributes itself throughout the medium, and then we have a single sink. So at that source and sink, the pressure is just going to be the same. So the pressure drop across the mediums are going to be the same. So we use the homogeneous medium model to predict the pressure gradient across just a fine layer and just a coarse layer, and then we equate the pressure drops across them. And to get the shear rates through each layer. And then we can back calculate from that to figure out what's going on in the entire stratified medium, and also get an idea of the relative flow speeds within within the layers. So once we do that and we run some calculations, I get the graph that I have here, where I've plotted a modeled reduce apparent viscosity as we change the Weisenberg number at different permeability ratios. Remember that the permeability ratio, in practice, the way we would modify the medium is by changing the bead diameters. For each permeability ratio, I've marked on this graph when the coarse layer becomes unstable and when the fine layer becomes unstable. And you'll notice that the coarse layer goes unstable at roughly the same spot, while the fine layer goes unstable at higher and higher Weisenberg numbers as we change the permeability. But ultimately, the development of elastic turbulence in these stratified systems are all roughly the same within experimental error. So what's practically relevant for us is this graph that I have here. So what the Healy-Shaw setup was interested in comparing the relative flow speeds between the fine and coarse layer. I've taken an extra step here by taking the observed relative flow speeds and comparing that against the laminar flow speeds that we would otherwise get if there were no polymers. What we see here is something we can use to interpret what's actually happening in the Healy-Shaw setup. So at a low Weisenberg number, we're just at laminar flow. There's no flow redirection. It's as we expect. As we increase the Weisenberg number, we hit the point where the coarse layer goes unstable, at which point that coarse layer, just that coarse layer, is experiencing increased resistance to flow. So as we further increase the Weisenberg number, that flow is hitting that wall of that increased resistance and is being diverted to the fine layer. And as we increase the Weisenberg number, that effect keeps on happening until the fine layer reaches a high enough flow rate where it itself also goes unstable, after which this effect disappears. And in practice, what we can do is we can take the medium characteristics, we can use this model by taking the medium characteristics, and if we want more flow into those low permeability layers, we can optimize some Weisenberg number we can choose a Weissenberg number to achieve the most amount of flow redirection. So what I have here are images on using confocal microscopy. We've added fluorescent flow tracers to the flow and have looked at what the flow actually looks like in the fine and coarse layers. And what you'll see is that the fine layer has very clear stream patterns, whereas the coarse layer is a lot murkier, indicating chaotic flow. And this is happening at a Weissenberg number where we would generally expect some instability. So in this case, we're seeing direct evidence that the coarse layer is unstable, the fine layer is not, and at a macroscopic scale, that's causing this flow redirection. So that flow redirection effect is this project, but all these experiments were conducted using a single solution, and naturally we might want to vary that solution. So we want to figure out some way of generalizing the behavior of these polymer solutions in porous media. The graph I have here on the left is compared to the original. I've added to achieve higher concentrations. On the right here is a less processed version of that same confocal microscopy, where I just have these flow tracers to see what's happening. And in this case, because the Weissenberg number is very high, I see quite a lot of instability in the flow. So that's everything. Thank you for listening.
So what's the Weissenberg number?
So the Weissenberg number is, it's a dimensionless number we use to characterize the strength of elastic forces. So with the Reynolds number, for example, like that's used to characterize like whether or not our fluid is in like a laminar regime versus an inertial turbulent regime. In the same way, the Weissenberg number is used to characterize if our flow is in a laminar regime versus an elastic turbulent regime, where we see flow instabilities because of the polymers being.
So which properties are affecting that number?
Oh, right. The way the Weissenberg number is calculated is based on rheology measurements. So a normal stress over a shear stress of the polymer solution.
I'm sorry. You want to say?
Sorry, and the normal stress captures that the elastic forces. The shear stress captures viscous forces.
And the other question I have, how much of the dissolution of the polymer happens as you put it in the water? Is it fully dissolving? What's happening to it?
Yeah, so the polymers, we wait until the polymers have fully dissolved in solution, so the solution itself is homogeneous. In terms of the amount of polymers we add, these experiments were conducted with 300 parts per million by mass of polymer in solution.
So did you consider simpler effects like time-dependent effects and shear thickening effects by the addition of the polymer before actually attacking the, I would say viscoelastic effects?
Yes, so the polymer, when we add the polymers into the solution, we see shear thinning, and from that we would expect, like as we increase the shear rate, we would expect lower viscosities. What we're seeing is like at sufficiently high shear rates, we see a jump in the viscosity, and that's what, and yeah, we attribute that to viscoelastic effects. Yeah.
Thank you.
All right, thanks. So 2 quick questions, I guess. So unless I missed it, what's the polymer and how does polymer chemistry affect this? And also, I guess I'll just ask both now. In terms of your contribution, did you do the experiments and these modeling development?
I didn't do all the experiments. I contributed some to the experiments, but most of my contribution was doing all the theory and modeling stuff. Yeah. To your, the polymer I'm using is hydrolyzed polyacrylamide. And, sorry, what was the other part?
How does, let's say, changing the chemistry of the polymer, how would that affect this a lot or not very much?
So it's mainly based on so this is related to the generalization that I was talking about in future work. So we consider like solvent quality as an example. So how much does the polymer prefer being with itself versus the solution, and that affect versus the solvent, I should say, and that affects how much elastic turbulence we're going to get, because this effect comes from polymers linking up.
Mhm, mhm. Right, right.
I have to stop here.
Okay,
I'm so
yeah,
sorry.
that's fine. Thank you.
Thank you.
Thank you.